Morning, Darcy. Okay, you notice that there has been some change of plan. Uh, as we discussed last week and agreed, I have moved the third practical in week 10. So that gives you more time in completing this task, given that this one is worth of 10% of your total mark. So doing that in week 10 give you more time to complete and of course help you with getting a better score. All right, so now we have also Nguyen joining us. So yes, this week I'm going to give you a lecture today. We have demonstration tomorrow, and on Wednesday we go to the computer lab. Yeah, I have to mark that yet. Sorry, I've been busy with too many markings. So yeah, soon I would mark that. Thank you, Darcy, for reminding. Yeah, don't worry. I'll take care of that soon. But this Wednesday, we are going to have the third lab. All right, so let's get started with the lecture. And tomorrow we have demonstration. Wednesday, you go to the lab in TD320. And over there, we complete the last lab we have for this unit. Okay, so as I mentioned, not everything in terms of the beam can be investigated simply based on the forces. The forces are not adequate for finding the critical point inside the beam. So we know that a beam is generally subjected to three different internal forces. So whenever there is a beam, there are three types of internal forces. So I give you a simple example here. So that beam is subjected to axial load, one load in the middle, P1, P2, and it has two supports, A, B, right? So this beam, with the coordinate systems being selected here, there are three internal forces. I mean, if I make a section at the arbitrary section measured from here, X, here the internal forces are N of X, V of X, and M of X. So which one of these is more critical? Well, we can plot them, and by plotting, we find out the maximum value for N, maximum for V, maximum for N. But these are not of the same criticality level. Some of them, they're more critical. And morning, Chaisal, the only way we can find out which one is more critical is by introducing a new concept. The new concept is called a stress. So a stress is defined as force divided by the area. And right, so here I give you an example. That is a rod, force of P. So the area, I can make this area selected here. So if I cut that member, I'm going to have a stress developed here. And this stress is intensity of the force, stress. And unit for that is Newton per square meter. All right. So stress is force divided by area. And then for each of these three internal forces, you can define an internal stress. So then the internal stresses can be compared together, and from that we find out which one of these three are more critical. So today I am focusing on what stresses are developed due to the bending moment. So bending moment is making some stress here. Also, we consider what stresses are developed due to the shear force. And we talk about this in an average sense. So average means if the stress is uniform over the entire section. But in some cases like bending, the average stress is not useful. The stress would change from different values of the y. And that stress, we show that by sigma is function of not only x, but also y. So let's get started with the concept of the stress. These are coming from chapter 7 and 27. And this is chapter 7 from your textbook. Okay, so this is a rigid body object, and we know that if a rigid body is under equilibrium, all external forces can be simplified into one single resultant force and one single bending moment, or couple, which is lumped at one single point. And these are producing force intensities or stresses over all different cross sections. If we take three perpendicular areas like the one shown here, on each of these faces you will be getting some stresses. So the force can be resolved into three components, and each component divided by its area would generate a type of stress that is Newton per square meter. Some of these forces, they are coplanar with their plane, like this one, Fx. So this Fx is coplanar with this area here. So if the force and plane are coplanar, the stress is shearing stress. We show that by tau, that's a Greek letter. If the force is normal to the area, like this one, that is shown by sigma. And in either case, these are force divided by area. But when do you use tau? That is when force and area are coplanar. And when the force is perpendicular to the area, the symbol sigma would be used for that. And this is called the normal stress. Tau is the shear stress, sigma is the normal stress. Of course, this is the most general three-dimensional case. Fortunately, in this subject, we only are limited to the two-dimensional cases, which is far simpler than that. But keep in mind, in general three-dimensional case, you have on each face, you will have one normal stress and two shearing stresses. So that's the unit for stress. That is either Pascal, which is Newton per square meter, or Newton per square millimeter. If you keep all the dimensions like I, area, y, if you keep all of these in millimeter and keep the forces, whether they are torque, Newton meter, or shear, which is Newton, or normal as Newton, if you keep everything in Newton and millimeter, the stress would be megapascal. And if you keep all dimensions in meter and forces in Newton, then the unit would be Pascal, which is Newton per square meter. All right, let's start with the most simple case. The most simple case, like I showed you, is you are pulling a part in a two force member mode. And here I can define an area here. This area is perpendicular to the section. So therefore, I'm using this symbol sigma. That's the axial or normal stress. And that is the amount of the force divided by the area. So that is either Pascal, megapascal, but that is a normal stress. That is, we refer to this as internal stress. So far, you're familiar with the internal forces. Now we are introducing internal stress. So with the internal stress, the evaluation of how material behave and whether the material passes its limit, whether it's going to break or it survives the loading, we only know that when the stress are calculated. So stress, that is called internal stress. It could be axial, it could be shear. The example which I provided you here, this is a normal or axial stress, which is shown by sigma. That's a very simple case, and then the stress is represented as an average stress. So this is an average. It means over the entire cross section, the stress doesn't change. That is fixed. All right, so now let's go to a problem. I have a problem for you. Please, everyone, I give you 5 minutes. In 5 minutes, would you just try to find stresses inside cable AB and BC? So 5 minutes. Just let's take it. Okay, so this problem, this is not a beam. This is all members are uniaxially loaded. So it's easy to find out the internal forces. How do we find the internal forces? That is by free body diagram. So let's calculate the forces first. And there are two approaches to find out the forces. The first is by, well, first I have to make a free body diagram. Okay, so this is my free body diagram, and I can either choose the Cartesian method. Cartesian method, you have to break the forces into components and set net forces horizontally equal to 0, net forces vertically equal to 0. There are two unknowns, you can solve them. The other approach is you can do a construction by triangle. So you first you do this vertical force of 784.8 Newton. And then from end of this one, I draw a line with a 60-degree angle. That is the direction of the FAB. And from the beginning, I draw a line parallel to that line. So this is FBC, and that is FBA. So this triangle can be easily solved. This one is 30 degrees angle. That one is a this and this. They are 3, 4, 5-degree angle. So by solving this triangle, I find out the forces FBA and FA calculated. So both forces are in tension. So by solving this triangle, you find out the forces. And then the next is you have to find out the stresses in each cable. What type of stress is that? This is every cable has a circular cross section. So I know that the diameter of AB is 10 millimeter, and I know the diameter of the BC is 8 millimeter. So that means even if I apply the same load to the cables, one of them is going to be weaker than the other one because the diameter is smaller. So if you remember from last week, the performance of a structure, it's not only a matter of internal force. So internal force is only one factor. The second one is geometrical properties like cross-sectional area, like moment of inertia or center of area. The third one is material. So you can make a judgment whether a structure can take a load or not. First, by knowing the internal force. Second, by knowing the geometrical property. And third, by knowing that what force is there. All right. Okay, in this case, I know the internal forces. What about the geometrical properties? I have the diametry. So let's find out the internal stresses. So internal stress. In this case, the force is perpendicular to the cross-sectional area. So I'm using the term sigma. So sigma is the stress of AB. That is the internal stress within normal internal stress inside AB. And I also can find out normal internal stress over BC. And then these, I only have to divide the forces in Newton, 63.2.4 Newton. And this one, 395.2, this one is Newton. And what about the area? The area of the AB is pi by 4 d squared. Pi by 4. And by doing that, you find out the stresses in each member. And if we calculate the stresses, so within BC, within AB, the stress is 8 megapascal, and within the other one is 7.8 megapascal. So I noticed that stress inside BA, yeah. I show you how. No worries. Yep. All right. I show you that. Let me go back to this one. That's back to the first part of the unit, but never mind. So here in this triangle, you can apply the method of you can use the shine law. That is, you do need to have the angle here. You do need to have the angle here. So what is this angle? Let me solve this triangle. 4, 5, 3, and here this alpha is tan inverse of 3/4. Okay, and then if I have alpha, then I can calculate this is alpha. Then I can calculate 90 minus alpha. All right. So I have this angle, I have this angle, so the opposite angle can be calculated because the internal angles of a triangle, the sum of the internal angles are 180 together. So that you know all the internal angles. And then applying the shine law, that is 784.8 divided by this angle beta, sine beta, which is equal to FBC divided by sine 30, and that is equal to FABA divided by sine 90 minus alpha. And then first you solve that equation. The only unknown is FBC. So that one would give you FBC. And then you solve that with this one, and that gives you FBA. Is that enough, or you want me to go to more detail? Chaisal, are you happy with this explanation? All right, thank you, Chaisal. All right, now you know how to find the forces, you know how to find the internal stresses, and AB is slightly, the stress is 8 point something. This one is 7. This is slightly smaller than this one. So which member is more critical? I mean, if they are made of the same material, the one which has a larger stress is more critical. All right, so that is a complete evaluation of the cables, not only by finding the internal forces, because once you know the internal forces, yes, one of them is larger, but their geometry are not the same. What about their material? So at this stage, I'm assuming that both of them are made of the same material. So if I know the internal force, the only thing I need is the geometry. So combining the internal force and the geometry, that give you a stress. Stresses are comparable. So to compare, I know that the stress inside the BC is equal to 7.8 megapascal, but inside BA, that is 8 megapascal. So the one which has got the larger stress is more critical. Okay, any question? Is that clear, or do you want me to explain again? All right, thank you, Shaisal. Let's go to next topic. All right, I mentioned that the comparison requires 3 inputs. First input is you need to know internal force. Second, you need to know the geometrical property. Geometrical property, these are like area, like moment of inertia, like center of area. All right, this is like Y bar. So all these are classified as geometrical properties. Later on, I introduce a geometrical parameter called Q. So that I explain that later, but all of these are classified as geometrical property. The third one is material. Okay, so if in this problem I had one of these cable made of aluminum, the other one made of steel, even though if the stresses are compared, that is not enough. So how can you utilize material to make a judgment? Okay, material, you have to do some performance tests on material. So that test would show you the limit of the material. The test is called tensile test. Tensile test is a very common test that is done inside most of the structural mechanic labs, laboratories. So in that, you have to make a standard sample out of the material. Most of the cases, metal, plastic, or even wood. So this sample, if you put that inside the machine can measure the amount of the load which is applied here. By increasing the load, the machine would measure the elongation of the sample or change in the geometry of the sample. So in this case, you see that the middle of the sample becomes narrower. This is called necking. So by simultaneous measurements of the force and displacement, so you can plot a diagram. That diagram is very important for material. So the diagram, we don't utilize the force. We use the normal stress because normal stress is more comparable. The force, internal force is not adequate. So in one axis, you have the internal stress, normal stress. In the other sample, you have, in this axis is a percentage of the elongation. Percentage of the elongation is delta L divided by L. So that they call this a strain, and they show this with epsilon. So if the measurements of the machines are recorded as a stress versus a strain, in most of the material, you notice some important observation. So the first part, the changes are linear. So this is the reversible part of the material. This is like a spring. If you pull a spring, it becomes longer. When you release it, it contracts. It comes back to the original configuration 0. But if you increase the force, the spring would permanently become elongated. And even if you remove the force, it won't come back to the same position. It would have some permanent deformation. Beyond some limit, the material would keep deforming. And then from here to there, that is not of interest for a structural engineer. These are too dangerous. Any structure, even that yield point, is too dangerous. You never want to get to that yield point. You want to limit the force such that it won't go beyond that point. So for example, if that force is half of this limit, then the safety factor of the loading is 2. If this load is 1/3 of the yield limit, then the safety factor, that is applied load divided by the yield load. So if this load is 1/3 of the yield load, then the safety factor is equal to 3. That means this is a very safe structure. The larger the safety factor, the larger. Imagine in a building, whether this is a bridge, whether this is an airplane, you just limit the amount of the load to be much lower than the yield limit. So that portion, this is called the safety limit. And for every design, by safety limit, you can control how safe your structure is. Okay, from this diagram, I mean, material scientists, they can make lots of conclusion, lots of observation. But as far as you are concerned as a structural engineer, you only want to know the yield limit. So every material, whether this is a steel, hardened steel, mild steel, concrete, wood, timber, aluminum, high strength concrete, they are characterized by a yield limit. And of course, the yield limit for steel, that is about 3 times higher than that of the aluminum. Concrete, this is not that weak, but very interestingly, concrete in tension is a very poor performer. It breaks, but in compression, it relatively is good. It's better than the timber, uh, poorer than aluminum, and poorer than steel. So I mentioned, let's go back to my initial 3 factors here. You want to decide how good a structure performs. You not only need to know the internal force, you not only need to know the geometry, also you need to know the material. Because by knowing the material, you go to this table, and the table tells you the limit of that material. The limit is expressed in terms of the normal stress. Comparing this limit with the current internal stress, you can find out the safety factor. You can find out whether your material is below the limit, at the limit, or above the limit. If that is above the limit, too bad. At the limit, that's marginal, too critical. Below the limit, yeah, that's good, that's safe. And then you can calculate the safety factor. Okay, everyone is with me. Just please give me a feedback. Shall I proceed, or do you want me to explain again? Any feedback would be appreciated, not only those who follow. I'm waiting. Yep, thank you, Shaisal. What about you, Nguyen? Forty, Darcy? Okay, no feedback from Darcy, no feedback from Nguyen. That's fine. Okay, thank you. Thank you, Darcy. Thank you, Nguyen. Let's go on. Now we want to apply this understanding to a problem. So in this example, I want to, this problem, it is a bar which is subjected to 2 forces, 7 kilonewton. And I know that I want to find what should be the diameter of this, such that, and then I know that this is made of the mild steel. Okay, for mild steel, I go to the table, and mild steel can take up to 250 megapascal, all right? So let's come back to this slide. For mild steel, 250 megapascal, that is the limit. And I know that in this cross section, if I make a free body diagram, the force is 7 kilonewton. I put that in Newton and keep the area into millimeter, such that the result become in megapascal. Remember, Newton plus millimeter, that gives you a stress in megapascal. And Newton plus meter, that gives you the result in pascal. So 250 megapascal, right hand side, we keep everything in millimeter. And because this is a round cross-sectional area, the area is pi by 4 diameter squared. And in this expression, left-hand side is the limit of the member. So this is a marginal design. Marginal design, that is, I set the strength of material equal to its yield limit. If I would have set this below the yield limit, the safety factor was larger than 1. But this is marginal with a safety factor of 1. So here I can manipulate that expression. The only parameter is diameter, and diameter is found to be 5.97. And why should I round this to 6? Because 6 makes this more conservative. If I round this down, that is not a conservative rounding. So I just make a larger value to make the structure safer. It's a minor safety, but it's better than not having a safety. Okay, any question? Question? All right, now we completed the average normal stress. The next topic is the shear stress. I mentioned that if the force is coplanar with the area, the mode of breaking would be shear. So shear is like a scissor action. You know what happens when a scissor cuts a material or breaks a material. I'll show you what happens. So I'm exaggerating a paper, right? And also I exaggerate a scissor. So that scissor applies a load, or let's call this V. This is the force, shearing force. And then my paper would cut through this area. So this force V is coplanar with this area A. So here my stress would be V divided by A, but because they are coplanar, I show that with Greek letter tau. The unit is megapascal or Pascal, but the symbol is tau. This is the shear force. This is the area, and that's the shearing internal stress, internal shear stress. All right. So now we want to introduce the concept of the shear stress. So shear stress. So can you tell me, this is like a karate. Karate, people do some stunt by applying an impact force in the middle of this brick. The brick would go through crack through this area. Two areas are being here subjected to fracture. So both forces are coplanar with this shear force. So this is my shear force. They are coplanar with this area and this area. So if I want to find that shearing stress, I either have to divide V divided by 2 area, or if I make a free body diagram, my free body diagram, this is the shear force, this is V by 2, this is V by 2. Then on each surface, the stress here is V by 2 divided by area, which is V by 2A. Or over here, I get the same thing, V over 2A. So either way, either I take the half of the force divided by area on this area, or I take one force distributed between two areas, one force distributed between two areas. Both of them, they give you the shearing stress average equal to V divided by 2A. Question? Any questions? All right, so now let's do one example here. Here I've got something which is called lap joint. Lap joint, for example, here I'm connecting two strips of metals or two strips of the wood together. And then here my shear force is equal to F. And in the left-hand side, can you tell me what is the shearing area? What type of shearing area we have on the left? Nguyen, can you tell me what type of shearing area I have on the left figure? So the only part of this structure which resists that shear force is the cross-sectional area of the bolt. So that cross-sectional area, which is pi by 4 d squared, yeah, the part in common, yeah. The only part of this structure, I mean, in the left-hand side, I assume that they are not glued together, they are not welded together, they are only being bolted together. So the cross-sectional area of the bolt is the only part of the structure would resist against the shear force. So here, if I want to find the shearing stress, my shearing stress would be V divided by the area of the bolt, and that is a cross-sectional area. But on the right-hand side, I'm just using some glue to fix two planes together. So the glue would be applied to this area, so that has an area of glue. And in this case, my shearing stress average is equal to shearing force divided by the area. This time is the area of the glue. So we know that the larger the denominator, the smaller the outcome. So here I can say that T of wood is smaller than the stress of bolt. Okay, the smaller the stress, that is the smaller the intensity, that seems to be safer. Is that right? Do you think that the wooden joint is safer than the steel joint? Can you justify? Can you give me a yes or no, or justify? Let me ask this by posting a vote. Okay, can you please respond to this poll, please? Okay, I have one response from, okay, Chaisal, yes, Porti, yes, Nguyen, no, Darcy, no. The correct answer is no. Why no? Darcy, Nguyen, can you tell me why wood is not stronger than bolt? Yes, correct, Darcy. Wonderful. Thank you very much for that precise answer. Darcy answer is correct. Because on the left-hand side, even though the stress is larger, but that larger stress, because this is made of the steel can take up to 250 megapascal. So don't let that large number scares you, because steel is very strong. If on the right hand side, we haven't listed the yield limit of the glue. What is the yield limit of the glue? The yield limit of glue, that is something like, I mean, in the best case scenario, if I list glue here, that would be something like 1 megapascal to 10 megapascal, right? It's still much, much less than steel, even though the glue would develop smaller stress, but because the glue is much weaker than the steel, you have to compare them with the reference number. The reference yield value of the steel is 250. The yield standard value of the glue is something like 1 megapascal. So the correct answers by Darcy and Nguyen. Appreciate that. Everyone, are you happy with the answer? Are you happy? Can you agree with that? All right. Thank you, Chaisal. Thank you, Porti. Now, let's go with the rest. So this one, is this a double shear or single shear? How many areas? Only one area is subjected to the shear, so we call this a single shear. So this is a single shear problem. So this is a single shear problem. And now let me show you something which is called double shear. Double shear, I'm applying the same force, but that force is distributed between two areas. So here, if I want to calculate the shearing of the bolt, that is either F by 2 divided by area of the bolt, or that is force divided by 2 area of the bolt. Both of them, the answer is the same. For this one, I either can find the shearing stress of the glue is equal to half of the force divided by area of glue, or force divided by 2 area of the glue. Both of them give me the same answer. So this is classified as a double shear. So most of the shearing stress problems you solve in an average sense, they are either double shears, single shear, or in some cases, rare cases, might be triple shear problem. You have to identify what type of problem that is, and you can answer this by making a free body diagram. Here, if I make a free body diagram, so my free body diagram would be like that. Left hand side, I apply F. Here, I should have F by 2, F by 2. So that is a double shear. On the previous problem, if I make a free body diagram like so, if this is F, that one is going to be F. So this is single shear, this is a double shear. Okay, so now with the next example, please listen very carefully. Are you ready? This example is examinable. I hope you know what I mean, because that's a very good combination of normal stress and shear stress. So here I have the left hand side made of a rod of a left. This one is rectangular area of the right. And these are normal stresses because the force divided by that area, the very same force divided by that area. And here I can see that stress over here is smaller than stress over left, okay? And then what happens within this pin? The pin is subjected to double shear. So one shear over here, another shear over there. So two areas here, area of pin. So the very same force divided by 2. This is double shear. So eventually you have to compare a stress due to that, a stress here and a stress here. So this is shearing stress, this is normal stress, this is normal stress. So you have to compare 3 different values together. And here we've done that for the left one, the stress is 3.98. For the, this is for the left, that is for the right. For the right, you get the stress 5 megapascal, and 7 megapascal, and for the shear, you get 5 megapascal. So that is now easy to compare. Which one is more critical? The one in the 30 millimeter, that is more critical because the amount of the stress is larger. I mean, I'm assuming that all of them are made of the same material. If they were not made of the same material, then you had to compare that with their limit, yield limit in the table. Questions? No questions? All right. Now, everything I discussed so far, these are in terms of the average. So I talked about the average normal stress, and I talked about the average shearing stress. So what does it mean is, if I'm pulling a rod, so at this end, if I magnify the stress at that end would be uniformly distributed. So everywhere inside that cross section, they have the same amount of the stress in an average sense. But in the bending, when you bend a beam and then you cut through here and you want to watch what kind of normal stress develops here, unfortunately, the normal stress is not the same. Because tell me, the points which are sitting on the internal fiber, are these under compression or tension? 40, the one on the inner radius, are these under compression or tension? 40. So compression for this point, that is negative value. So what about the fibers here? When you bend that, is this under tension or compression? Nguyen, is that tension or compression? So the fibers which are at the bottom, they are under tension, and tension is positive. So at the top, you have the fibers under compression. At the bottom, you get the fiber under tension. So if you want to go from a negative number to positive number, there should be somewhere in the middle. We call that the zero. So you can't go from negative to positive without passing through zero. So that is a distribution. I mean, that is my beam cross section. So the negative value is something like this stress, and the positive here is like that. So somewhere in the middle, that is the neutral plane or neutral axis. So here stress is zero. And if that changes linearly, it goes like that. So the lower fibers, the farther they are from the neutral plane, the larger tensile. The upper fibers, the farther they are from the neutral, they are larger in compression. And then the variations are linear. So that is the internal stress due to the bending. Internal stress due to the bending. We use the very same symbol. We use sigma to say that when a beam is subjected to the bending, these are how stresses are developed. By contrary to the starting examples, this is not a uniform. The average here is going to be zero. So that zero doesn't make sense, right? Because if you take average between -10 and 10, the average is zero. Here, your stress would be not only the function of x, it also would be a function of y. So here, your sigma is function of x and y. It means when you move in the x direction, your normal stress would change because the bending moment changes. And also when you move in the y direction, also your stress would change. So average is not useful when you are looking into the stress produced by the bending. Okay, who is with me? Please give me a feedback. Can I proceed? If you want me to explain again, please just all you have to do is ask. Don't be shy. If you don't understand this, just let me know. I'm happy to explain again. Any feedback, please? All right, so here, thank you, Nguyen. Here we have a example. I've got a beam before and after bending. So before bending, I'm using some grid. Thank you, Shaisal. Thank you, Nguyen. I'm using a grid. So this grid is useful to tell me that due to the change of radius, that's when you bend a member, the radius of curvature changes, right? So before bending, I'm dividing the beam into a number of grids. So these grids would help me to understand. So, right, the fibers at the top, they are subject to the compression. That is with the positive bending. This is a positive bending because my beam is laughing. When the beam laughs, this is positive. If the beam cries, that is negative. So with the positive bending, I apply the load in the top, and the upper fibers, they are under compression. The lower fibers are under tension. And right in the middle, I mean the neutral axis. The neutral axis for a rectangle is right in the middle. If that's a triangle, the neutral axis is 1/3 from the base, 2/3 from the apex. If that is a circular cross section, you have to find the center of area of the cross section, and your neutral plane passes through here. Remember that we discussed last week. So whatever the cross section, under positive bending, the fibers at the top are under compression. The fibers at the bottom, they're under tension. and the fibers located inside the neutral plane, neutral axis, they are subjected to the zero normal stress. All right, so this is a general cross section. The general cross section could be anything: circle, oval, rectangle, I section. So for each of these shapes, even if they are a composite section like an I-beam, you are able to find their geometrical parameter. Geometrical parameter, I mean y bar, area, and moment of inertia. Later on, we introduce another geometrical parameter called Q. So that to be covered next week. For now, you are familiar with these three geometrical parameters. All right, so subjected to the M, what happens when you apply M? This is called internal normal stress due to the bending. Internal normal stress due to the bending. And I know that this is not only the function of X, it's also a function of Y. It is function of both X and Y. It means if I want to find out which point is critical, it's not enough to say, look, at this very particular X, that is the amount of the bending. All right, that is not enough. You also have to find the variation in the Y direction to find out what sigma is maximum for the entire beam. The maximum, which is sigma, which is maximum, the normal stress, which is maximum, is likely the point at which the crack would grow. As a structural engineer, your job is to find out which point at the structure can grow the crack first. That is the most critical point. And in finding that, you not only rely on the X, you not only rely on the M of X, the plot of M of X would tell you the maximum M, right? That is how X would help you. But what about Y? If I tell you that this is my neutral axis, and above neutral axis, this is compressive, this is tensile. So yes, in the Y direction, my normal stress would change. You have to find here is maximum or here is maximum. All right, so I'm going to give you a formula. That formula is the first important equation for your final exam. In your final exam, there are two important equations. One of them is called flexural formula. So flexural formula is how this normal stress is calculated. And then that is my normal stress due to the bending is proportional to the bending. The larger the bending, the larger the stress is proportional with the distance of the point from the neutral axis. So if I'm interested in a stress in this point, I have to measure how far this point is from my neutral plane. So that is Y, and that is proportional to the bending moment of inertia. Directly to the M, directly to the distance from the neutral plane, reversely proportional to moment of inertia. That is called flexural formula. And that is the first most important number one equation for your final exam. The second important formula, that is due to the bending, due to the shear force, what shearing stress is developed as a function of X and Y. That I would cover next week. For this, that is for today, and that is for tomorrow tutorial, and that is for your lab 3. Lab 3. In lab 3, what we do is I give you a beam which has a C section. So this is my beam with a C section. right? And then you apply a load here. This beam is sitting on the top of a two rollers. This is simply supported. So you find the reactions here, and then you have to find out the moment of inertia of this one. You can calculate the amount of the force, and then I ask you to find stresses here, and stresses here. So I give you few points, point 1, point 2, point 3, and then I ask you, can you measure these stresses? So what you do is you find that moment of inertia for the section. All the dimensions of the beam you can measure in the lab, and this is a composite section. For that composite section, how do you calculate the moment of inertia? First, you have to decompose that into two shapes. One big rectangle, one small triangle. That one minus this one. That is your. But then you have to find out the neutral plane axis. This is y bar. And with this y bar, when you are calculating these, you take that from the table, I1, I2 from the table, and then you add a penalty to this one, D1 to A. You find the penalty for this one, D2, A2. Okay, so that is how you find the moment of inertia. Once you find the moment of inertia, for every point, you have to measure, I mean, this is P1, P1. What is the distance of P1 to here? Okay, you find that distance, Y1. What about the distance of the second point? The distance of the second point with neutral planes, that is Y2. And for the third one, you find Y3. So for each of these points, how you calculate the stress? A stress in point 1, that is the bending moment here. So you have to plot the bending moment of this one, X, Y. You plot the bending moment. At this point, the bending moment is M1. And you measured Y1, you calculated I. So that is the stress. You do calculate the stress in point 2. That is, at this point, you find out the bending moment multiplied by Y2 divided by I. And for the third point, you do the same thing. So that is your third lab. You calculate few normal stresses due to the bending, and then I will give you some experimental measurements. So you have to compare your calculated values with the experimental numbers, and that you write a concise report comparing and making discussions. If they are different, you explain where the errors are coming from. Okay. Do you want me to explain this one more, or how to get Y? Well, good question. Good question. All right. So let me be specific. All right. Let me be specific. And I just respecting those who are attending the class, I'm going to take you through the instruction page. And this is like a kit. If people are watching this video, you're welcome to use my instruction for okay, so this is, you go to the lab and this is your instruction page. Here is the cross section. All right, for this cross section, chase out, what you need is the neutral plane. That's a composite section. How do you calculate the composite plane? You find how far that neutral plane is from the datum. This is the datum. So once you have this cross section, once you have this neutral plane, you can find out the moment of this surface. The moment of this surface is what? So I, for this one, is a big one minus a small one, right? So this is I bar 1, this is I bar 2. And these are with respect to the where? These are with respect to the center of this one, with respect to the center of this one. But these centers are not coincide with that neutral plane, for each of which this is D1, this is D2. So you calculate the penalty for this, a penalty with that. So you normalize. This is the parallel axis theorem. With the parallel axis theorem, the first task is you find the I. I believe everyone can find the I. The next part is I have given you the position of these sensors. 1, 2, 3, 4, 5, 6, 7, 8, right? So here, all Y measurements are with respect to where? They have been given with respect to the DOTM reference. DOTM reference is at the bottom. So these values, you have to subtract them from Y bar, which you calculate in the first part. Does it make sense, Chase out? So each Y, and these tables, the Y values are given with respect to the bottom, which is the bottom surface here. But then that value, you should take it away from the Y bar. Y bar, you calculate this in the first step. So all these Y values subtracted from that, this is the Y value in the flexural formula. So here you have sigma of 1, for example, that is M1, you get it from the bending moment diagram. And for Y1, that is 300 minus Y bar, and then divided by I. I explained to you how to calculate I. That's by adding these two, or this is subtract, I minus this one, because this is a negative shape, right? So the second one is negative, the first one is positive. Chaisal, is that clear? Do you want me to explain more? Thank you, Chaisal. Anyone else? All right, so that is for Wednesday. This is for Wednesday. Let me go back to the remaining slide here. I mean, how do we derive the flexural formula? To derive the flexural formula is not examinable. I mean, I go through the derivation, but don't worry if you find that too complex. If you don't like it, that's okay. So y in the flexural formula, this is the distance between, I want to find the stress here. So I need to find out how far that point is from my neutral plane. So this is my y value. First, I need to find the neutral axis. That is y bar from the DOTM. And then you find the y value of the point for which you want to calculate the stress. And once you have the y at these points, if I know the bending moment, my normal stress at this point is m multiplied by y divided by I. That is flexural formula. Okay, when you do the bending, the inner part of the beam subjects to the compression, the outer fibers are under tension. I mean, here I'm assuming a positive bending, which is shown here. So how can we verify the flexural formula? There are two approaches. I mean, we can make a strip. So I can make a strip here. So at point X, I can slice a section. This one is X. This one is thickness of my slice is delta X. So I draw the free body diagram on this side, and by writing the balance of the free body diagram, which is a differential equation, I have to do the integration. That would give me the formula for flexural. But all you care is the flexural formula here. The bending stress is a function of m, and m is a function of x. It changes with x. Here is y. This is I is the same for the entire beam. So that is why your sigma is function of not only x but also y. All right. So yes, of course, if I decide to find out the stress due to the bending about a different axis, all I have to change is, yes, I need to know how much bending is there. But if my bending is about the y axis, then the distance, the x distance goes in the numerator. That is not a concern. You only do this type of problem in this unit for the final exam. But of course, if I bend it here, that is my mx. But if I bend it perpendicular to that, that would be my. Don't worry about that. And here I've got a photo. This photo is showing a timber which was subjected to the bending, and you find that half of the beam is showing the fracture due to the compression, and the lower half shows the fracture due to the different sign. So one of them is tension, one of them is compression. That explains why normal stress keeps changing in the y direction. And the variation is linear. So this is the linear. All right. So can you tell me, just by looking at this equation, I want to find in the y direction what is the maximum bending? The maximum is m is uniform for the entire cross section. M doesn't change, but if I pick my point here, what would be the y? If I pick my point along the neutral axis, nuyen, by picking a point on the neutral axis, what would be the value of the y? What is the distance of this point from the neutral plane? That is 0, right? So that means at this point, my stress would be 0. This is not the maximum stress. This is equal to 0. So if I pick it here, right, that's something like 30. Y would be 30. That is not maximum. If I pick the point at the outermost, y would be 60, right? So I'm concluding that with the beam subjected to the bending, the largest normal stress is the point which has maximum distance from neutral plane. Yes, if my section is a rectangle, the maximum distance is either here or here. Both of them are equal, right? These are equal. But if the section is a triangle, neutral axis is here. So which point has the largest distance? Is this the point A or point B? Which one has a, so this is YA, this is YB. And then these are going to the numerator, so I compare sigma at point A compared to sigma at point B. So let me write you a multi-choice question. I want everyone answer this question. So this is a section, a triangular section, and point A is at the apex, point B is at the base. Which one has got a larger bending moment? Okay, I got 2 correct answers from Porty and Darcy. What about Nguyen? What about Chaisal? All right, Nguyen is also correct. Chaisal is also correct. All right. So with a beam subjected to the bending, for one given cross section, the largest normal stress is at the point which has the largest distance from the neutral plane. Everyone agrees with that conclusion? So this is, we are generalizing that example. The example was for the triangle. For the case of the rectangle, the maximum stress is either at the top or at the bottom. They're equal absolute value, but one of them is positive, one of them is negative. If that is concrete, it makes a difference because concrete cannot take tensile, so the critical point would be the tensile value. But if that's made of the timber or steel, they have the same property on tension and compression. So therefore, for a rectangular cross section, the maximum stress of a rectangle is either at the top or at the bottom. But any other shape, depending what shape of the composite is, you have to decide whether the upper fiber has the largest distance or the lower fiber. It won't be anywhere in the middle. It's either the top or bottom. You have to make a decision. When I ask you what is the maximum normal stress in a cross section, a cross section is a composite beam. So the question is whether the top point is critical or the bottom point. And the only way you can answer this question is by finding the neutral plane. So the point which is farther from that neutral plane is most critical. Okay. Please give me a feedback. Everyone followed my conclusion. Thank you, Chaisal. Okay, everyone is happy? All right, so here we've got a beam of rectangular cross section. And if I tell you that this beam has a rectangular cross section with this dimension, are you able to calculate the bending moment? So you want to find out what is the maximum stress developed in this beam. So you have to find out the neutral plane. The neutral plane for rectangle is right in the middle. And then you need to find the moment of inertia for a rectangle that is 1 over 12 BD cubed. So easy to find I. And we want to find out what is the maximum M it can take. So I just have to manipulate the flexural formula. So if I tell you that sigma is equal to MYI, and then I ask you, can you manipulate that to find M? So M is equal to sigma I divided by Y. So here I know the sigma, that's the limit of the wood. I grab this from the table. So wood, according to that table, what was the limit of the wood? Let's find this out. Yeah, for wood, the limit is 5 to 20 megapascal. So let's assume this is 20 megapascal. I plug here 20 megapascal. I plug 20 megapascal here. And what about the I? I, we calculate this one here. That number goes here. And what about the Y? Y is either at the top or bottom. Y is 60. So I put 60 in the denominator, and this is 60. And then you find out that the bending moment, which is making that one to crack starting from here, that is 2.88 kilonewton meter. Okay, so you can find out this moment either by using the flexural formula as I did, or you just make a free body diagram and solve this free body diagram by integration. Either way, both of them give you the same answer. Okay, so today, what we did for today was we introduced the concept of internal stress. Internal stress is critical because a beam subjected to bending develops three types of internal forces, and these internal forces cannot be directly compared to each other. You have to translate the internal forces into internal stresses. And the way we calculate internal stress, there are two ways. Either you calculate the average stress, or you find the stresses which are variable. So today we discuss all the average stresses, whether they are due to shear or tension inside the two-force member, or in the case of the bending, we introduce the formula of the flexural bending. Flexural formula would tell you how the normal stress in beam due to the bending would change in the y direction. And we solved a number of examples for that, and that brings our lecture today to end. So here, is there any question for today's lecture? Any question, please? Okay, if there is no question, let me finish the attendance. I've got Darcy here, and Nguyen here, Chaisal here. And Porty. Okay, if there is no question, I will see you tomorrow in the demonstration class. Thank you, everyone. See you tomorrow. Thank you, Jaisal. See you, Porty. See you tomorrow. Thank you, Nguyen. See you tomorrow. Bye.